So how do we investigate kill kinetics? Well, that's actually really quite difficult because if you have a fast-acting biocide and you've only got 2 seconds, that requires a certain type of approach, scientific approach, which is not easily reproduced in many laboratories. In our laboratory, we use something called bioluminescence. And bioluminescence, most people will be familiar with fireflies, glowing things, glowing algae perhaps in the sea. Well, that is the nature of bioluminescence. What we're able to do is to take those inspirations from nature, so we harness those DNA abilities of those organisms, and we can transplant them into bacteria of interest. So for instance, we can do that with E. coli or Salmonella. What does this mean? This means, sort of cutting out a long-winded scientific explanation, is that when the bacteria is alive and well, or when it's metabolizing, it kicks out bioluminescence or light. Now that's really useful for us, and it's useful because we can detect light. So our hypothesis using these bioluminescent reporter bacteria is that if the lights are on and we can detect that light, that means that the bacteria is alive. If the lights go out, that's a really good indication that the bacteria is either dead or metabolically inactive. And if you think about it from a disinfection point of view, that's really what we're after. We're after either killing the bacteria or making the bacteria such that it cannot reproduce or that it's not very active. The second advantage of using bioluminescence is not just that it reports or tells us something about the living organism that we're applying the disinfectant to, but also we can visualize that activity over space and over time. And that provides us with a really powerful tool for visualizing the disinfecting or decontamination event. So in experiments that we've performed, we've transformed bacteria into bioluminescent entities, so they're kicking out light, and we've applied our disinfectant. And what that's enabled us to do is to model and calculate how fast these bacteria are killed when applied with a disinfectant such as electrochemically activated solutions. And in some of the work, we've shown that this kill is incredibly fast. That in itself is very interesting because it elucidates 2 things. One, it gives you, if you like, a very quantitative measure on how these disinfectants are effective in relation to contact time. So in many industries where cleaning is imperative or decontamination is imperative, contact time of the disinfectant and the thing that you're trying to decontaminate is imperative. It's imperative from a hygiene and health perspective, but it's also imperative perhaps from a business perspective because time equals money. So if you understand that process very well, you can model your cleaning regimes or decontamination regimes to fit a suitable model that is appropriate for your particular setting or business. For me as a scientist, an even more interesting aspect of using bioluminescing reporter bacteria is this idea of regrowth. Now this is incredibly important. So we may think we've disinfected a surface or killed a bacteria, but in reality, and you see this on many products, in reality we maybe have disinfected 99.9%. Now in most people's books, that's a pretty good hit rate. When you're dealing with 1 trillion bacteria, that 0.1% still represents a significant number. And if there's one thing we know about bacteria, and most mums and dads will tell you this who have children, is that bacteria multiplies and grows. So one interesting aspect for us in modelling or understanding disinfection is what does that look like? What does that regrowth look like? So if you think you've disinfected a surface, how do you know that that bacteria is not going to come back 24 hours later? And this is incredibly important in places like hospitals or intensive care units because what we know about bacteria is they're pretty smart and they're some of the oldest living things ever to have been around on planet Earth. So they're adaptive to their environments and they're really smart things. So what we're trying to understand is if we apply different types of disinfectants, how does that play out in terms of the regrowth of the bacteria that we're trying to kill? And what we're able to do with bioluminescence is to demonstrate this very visually. So I explained earlier about bacteria glowing and being alive. Well, what we can do with our experiments or in our facility is treat those bioluminescent bacteria with a disinfectant such as electrochemically activated solutions, and we can actually visually watch the lights go out, which would imply that the bacteria is either metabolically inactive or hopefully dead. What's even more interesting is that we can keep our low light cameras that detect this bioluminescence rolling. So what usefulness is that? Well, that means that we can come back the following day and see if the bacteria that we think we've disinfected has grown back. And in some of the work we've done, it's pretty apparent that many disinfectants do not have a residual quality about them or do not kill enough bacteria in the initial application, and that results in regrowth. What we've discovered with using ECAS is that that regrowth is very, very minimal. And if you look at some of the data that we've shown, you can see that glowing bacteria materializes for some disinfectants and some controls, but when ECAS is applied, that regrowth is virtually nil. And that's really what we're after, because ultimately it's sustainable long-term hygiene that we're after, as opposed to fighting this perpetual regrowth and rebirth of bacteria.